Picture a void. There is no background space, no grid, no manifold. There are only discrete, featureless events firing and linking together through brief, directed connections. In this framework, known as boundary condition quantum mechanics, time is provided operationally by a clock module called VII. Space, however, is entirely absent. What we see instead is an active slice, a short, fast-mixing window where these instantaneous connections form and vanish. The goal of the Stage 2 program is to look beyond this transient slice and find a persistent spatial cloth, a stable structure that survives the constant turnover of new events. We are attempting to derive a stable, reproducible geometry from a system defined by continuous, chaotic microscopic fluctuation. Space is not a foundational given. It is a structural pattern that must be mathematically extracted from the chaos of transient quantum events. The most logical first attempt to find space is to enforce strict persistence, a rule called HITS-2. This rule demands that exact edge connections between specific events repeat across multiple time bins to be considered real. Strict persistence fails, isolating small, disconnected motifs rather than a spanning spatial backbone. The solution is a pivot to permissive persistence, or HITS-1. Under this rule, a connection is retained if it appears even once in a given epoch. This permissive approach yields a connected graph. However, the exact microscopic edge identities are highly seed-sensitive, meaning the specific links fluctuate wildly from one simulation run to the next. This diagram showing a topographical wave helps reconcile the contradiction. Think of it like a vibrating bedsheet. The exact identity of the individual edges forming the surface represents molecular noise. It fluctuates constantly. But the macroscopic shape of the wave itself represents fabric deformation, and that coarse geometry remains completely stable. To define a spatial cloth, we must abandon exact microscopic links and let the data dictate an operative mesoscopic scale. To move from raw events to a persistent cloth geometry, we use a specific analytical pipeline. The first operation isolates the connected, undirected projection of the HITS-1 core edge set. The critical mechanism for coarse graining this data is an algorithm known as Louvain community detection. This widely used algorithm extracts community structures from large networks by optimizing the density of connections inside clusters compared to connections between them. Applying this algorithm partitions chaotic nodes into stable clusters. At high pressure, 22 communities emerge. Though microscopic edges fluctuate, macroscopic places remain stable. Next, we collapse these communities into massive supernodes, drawing directed, weighted edges to represent inter-community event flows. This supergraph data proves reproducibility. Normalized mutual information sits at 0.84. Unweighted edge set Jacquard overlap reaches 60%. Unlike the microscopic cloth's near-zero overlap, crossing edge weight correlations hit 0.91. Coarse graining rescues the data, providing a stable framework for measurable geometry. With a stable supergraph established, we can attempt to extract a geometric metric, such as an effective ball growth exponent. The raw microscopic cloth fails this test. It is topologically small-world and too heavily populated with shortcuts to admit a power law ball growth window. A radius search on the supergraph expands outward to measure neighborhood growth. Plotted data yields an effective growth exponent near 0.8. This sublinear slope confirms the emergent cloth is a sparse, stringy object, extracting stable operational geometry without a continuous background manifold. Does a mathematical graph matter if matter doesn't respect it? We have to ask, do particle-like threads move locally on this cloth? To test this, we log the thread events and map their shortest hop distances on the supergraph between consecutive time bins. This chart shows hop distance distribution, revealing strict movement containment. Probability mass concentrates at distance 1, hops strictly to neighboring communities. There is zero transition at distance 3 or greater. Threads are bounded to local motion, confirming the supergraph acts as a genuine physical substrate. The final stress test scales the ensemble size up to 32 events to see if the metric shatters. At this scale, the spatial geometry separates into a rigid core and an extensive fluctuating halo. This chart tracks bifurcation. Core fraction phi drops distinctly as the ambient halo expands, yet clock coherence remains robust, unaffected by spatial growth. Space and time decouple. We haven't built relativistic space-time, but proven that stable spatial locality emerges dynamically from relational coarse greening.